In today's video, we will be learning all about the electromagnetic interference of digital circuits. We are going to talk about the different causes of digital circuit EMI, including both common mode and differential mode EMI. And then finally, we will go over the different ways that you can address this EMI. So by the end of this video, you should be able to take these concepts and start applying them to your own designs. But real quick, before we go any further, feel free to give me a follow on Instagram to see some of my other content and check out some of the links in the description. You may find them interesting. And with that out of the way, let's jump right into it. So first, some quick background on digital circuits and EMI. Over the past few decades, there have been some significant improvements in the technology of digital circuits. This means higher clock frequencies, faster switching times, shorter rise and fall times, and more advanced functionalities that have all done wonders for the world of electrical engineering. However, these improvements in technology are not without their drawbacks. As a result of these technological advancements in digital circuitry, EMI has started to become a serious problem. It has gotten to the point where if you do not consider EMI early on in your design phase, it will be almost impossible to control later on down the road. No longer can we rely on some of the older, more antiquated methods to control EMI. So instead, we are having to develop new and improved methods to help address EMI right from the beginning. So before we talk about how to reduce the EMI in digital circuits, I want to go over what exactly I'm talking about whenever I use the term digital circuit. A digital circuit is something that operates in either one of two states, that is on or off, or 1 or 0. Typically, digital circuits are periodic, meaning they operate continuously, repeatedly generating these signals. For example, a square or sawtooth waveform. Common examples of digital circuits include microcontrollers, power management integrated circuits, and motor control modules. As I mentioned earlier, when it comes to the EMI that are generated by these digital circuits, there are two main categories. That is common mode noise and differential mode noise. And the way we mitigate these two types of noise differs. A lot of times we might have both common mode and differential mode noise present in a circuit at the same time. So we might be employing a variety of techniques to reduce and manage EMI in a digital circuit. So the first type of noise I want to go over is differential mode noise. Differential mode noise can be thought of as the noise that is simply a result of the operation of a circuit. The way it works is the current flowing around the loops that is created by the wires or copper traces in the circuit. Those will generate a magnetic field, and that magnetic field is where the EMI comes from. While it is not possible to completely eliminate differential mode EMI, it is certainly possible to minimize it using the techniques we will discuss shortly. But before we discuss those techniques, I want to give you an explanation of some of the RF theory behind differential mode EMI. For differential mode EMI, we can use a loop antenna to model it. The strength of a signal being generated by a loop antenna can be given by this equation, where A is the area of the loop, I is the differential mode current the loop is carrying, and F is the frequency of the signal on the loop. It is important to note that the shape of the loop has no impact on how strong of a signal it can generate. So it's only the area, frequency, and magnitude of the current that really matters. As you also may have noticed, there is a linear relationship between both the area of the loop and the magnitude of the current that it is carrying. However, and this is very important to understand, there is a quadratic relationship between the frequency of the signal and the strength of the magnetic field that it generates. This will become especially important later on when we talk about the harmonics of the digital signals and the frequency spectrum. So now that we know a little bit more about where the differential mode noise comes from and kind of what factors affect it, let's talk about some of the techniques that we can use to mitigate and minimize our differential mode EMI. In general, there are three main places that you can address EMI. One is at the circuit level, the other is at the PCB level, like the layout, and the third one is at the assembly level, so dealing with like your cables and any type of enclosure that you can put your circuit board in. For this video, we are going to focus primarily on the first two, as they are by far the most effective areas that you can address EMI at, not only from the size of the impact you can have on your EMI, but also the cost required to make such an impact. So for the PCB layout, there are two main strategies you can employ to reduce your differential mode noise. The first one, of course, is minimizing the loop area. This means doing things like placing your components as close together as possible, routing the traces in such a way that they are as short as possible and your current loops are minimized. In my opinion, the best way you can go about this is to just prioritize the loops that you deem to be most critical. In other words, the circuits that you think will cause the most EMI problems, focus on those circuits and prioritize the proper PCB component placement and routing for those circuits first. You'll want to follow your typical best practices for routing. So doing things like making sure your traces are as short as possible and having your return currents flow on a plane that is directly adjacent to your signal plane. Now, if simply reducing the loop area does not have a big enough impact, there is another technique you can employ, which is the use of canceling loops. And this diagram explains how they work. Essentially, what we want to do is print two loops directly on top of each other or adjacent to each other and have the current flowing through them going in opposite directions. What this does is essentially it creates two opposing magnetic fields that will cancel each other out. So on a PCB, you can imagine your canceling loops being placed right above each other on two different layers or right next to each other if they're on the same layer. Just make sure that they are carrying current in the opposite direction. Canceling loops are quite a neat strategy in my opinion, and I highly recommend you get familiar with them and know how to use them effectively. Because a general trend I am seeing with designing for EMI is that these best practices are just getting more and more difficult to follow as designs become increasingly complex and your frequencies get higher and kind of all the things we talked about in the very beginning of the video. Now, for the circuit design aspect of addressing our EMI, that's really going to focus on the choice of components that you use. In other words, think about components that you can add or change in order to improve your EMI performance. And for that, there are actually quite a few options that you have. The first circuit level change that we can implement has to do with controlling the rise and fall times of our digital signals. Now, to understand how this has an impact on EMI, we need to go on a quick tangent to explore more of the EMI theory behind digital circuits. Now, as we mentioned earlier in the video, digital circuits typically operate using periodic signals such as square waves or sawtooth waves. And if you're familiar with digital signal processing theory, then you may know that these square waves and sawtooth waves are really just compositions of sine waves. And this is where a mathematical analysis tool known as the Fourier series comes in handy. We can utilize this tool to shift from the time domain into the frequency domain so that we can analyze our digital signals across the frequency spectrum. Because remember when we talked about earlier that there is a significant relationship between the frequency of a digital signal and its EMI performance. Now, without going too deep into the Fourier series, the key takeaway that I want you to understand is that it will tell us the magnitude of the currents at each frequency across the spectrum. So imagine just a collection of sine waves, all with different magnitudes, and that is what we use to make up our periodic signals. This composition of sine waves can be thought of as the sort of noise profile of the periodic signal, and this will actually tell us what our radiated emission scans will look like. So bringing us back towards the EMI problem, so what it all boils down to is that the magnitude of the harmonics of those square waves will decrease linearly as the frequency increases. So you would think that our radiated emissions would also decrease, right? Well, that's not the case, because if you remember, there is a quadratic relationship between the frequency of the signal and the strength of the magnetic field that it generates. So that actually will overpower the decreasing current amplitudes and result in actually higher overall emissions, which sounds pretty bad for us, except for one saving grace. And that is, we live in reality and there is no such thing as a perfect square wave. So what I mean is there's no such thing as an instantaneous rise time and fall time. In fact, all these so-called square waves really look more like trapezoids with some finite amount of rise time and fall time. Now that might be in the order of magnitude of nanoseconds or picoseconds, but it's still finite, which means that the digital circuits are not actually generating square waves, but rather trapezoidal waveforms, and those have a very different frequency envelope compared to your perfect square waves with instantaneous rise times and fall times. Now, without getting too lost in the weeds about analyzing the Fourier transform of a trapezoidal waveform, the key takeaway is this. The trapezoidal waveform results in an emissions envelope that linearly increases until a certain breakpoint, at which point it starts to level off and remain constant, often to infinity. The location of this breakpoint can be given by this equation right here, where T sub R is the rise time of our periodic signal. So bringing us all the way back, by controlling the rise time of our periodic signals, we can significantly impact the radiated emissions of our digital circuits. So essentially, the longer our rise time is, the better our radiated emissions will be. So now I'm sure you must be wondering, how can we control the rise time and fall time of our digital signals? The short answer is by simply using a resistor that goes in series with our periodic signal. You may have seen these resistors in various types of digital circuits, such as digital communication lines, clock lines, and the gate pins of power transistors. We will actually cover the way to appropriately size and calculate the values for these series resistors in another video. But the general takeaway here is that a higher resistance equals a longer rise time, which therefore results in better radiated emissions. But one thing I would caution you about sizing the resistors for EMI is that too long of a rise time can actually impact the functionality of your digital circuit. So that's something to be careful of. A general rule of thumb is that the periodic signal's rise and fall times should not account for more than about 1/10 of the signal's period. And also note that for power supply circuits, adjusting that gate resistor on the MOSFET will also impact the amount of power it dissipates and therefore its thermal performance. So those are just some areas that you want to look out for, but we'll talk about those in another video. Another option we have for reducing the differential mode noise of a digital circuit is to increase the loop impedance. The reason why this works to reduce our EMI is that by increasing the loop impedance, we will reduce the loop current, and as you know, that has a direct impact on the radiated emissions. Now, I'm sure you're wondering, but won't increasing the loop impedance have a negative impact on the performance of the digital circuit? After all, we just got done talking about how having too large of a resistor can negatively impact the digital circuit's functionality. And you're right about that, which is why I use the term impedance and not resistance, because we want to adjust the circuit's impedance, more specifically the higher frequency currents that are flowing in the loop. And the way we do that is by placing a component known as a ferrite bead in series with our current loop. A ferrite bead is essentially just a specialized inductor that will act as a high impedance only to the higher frequency signals, and has been specifically designed for the really high frequencies that would be tested during like a radiated EMI scan. So in general, they will mostly leave your digital circuits, which operate at much lower frequencies, relatively untouched. You can find ferrite beads that have been specifically designed for all different kinds of applications. They have unique frequency responses, so definitely check out the datasheet of the component that you're thinking about using and make sure that it has a proper frequency response in the frequency range that you are targeting. This kind of ties into the design of EMI filters, which I will have an entire separate video that goes into great detail all about doing EMI filter design. But this is a pretty good starting point for now. The next circuit design technique we have is one of my favorites, and this is a technique known as clock dithering, also known as using a spread spectrum clock. This is a feature that a lot of modern integrated circuits come with, where instead of operating at exactly one single frequency, what happens is there is a low frequency oscillator that will slowly adjust the switching frequency of the digital circuit over time. It's enough to significantly impact your radiated emissions, but it's not enough to affect the actual functioning of your device. I really like this technique because it has several advantages. One is that it really doesn't cost anything to implement in your design. You just pick an integrated circuit that has this feature, and then you can just pop it right into your circuit. There's no like special design techniques that you really have to use when utilizing a spread spectrum clock. Circuits that employ these dithered clocks show significant improvements in their EMI performance, which is another reason why it's one of my favorite techniques to use. And then lastly, one of the more obvious but often overlooked strategies you can use to reduce your radiated emissions is to simply just lower the switching frequency of your electronics. As I mentioned earlier, technology has advanced quite a lot in the last few decades. But as a designer, as an engineer, what you should often be doing is asking yourself the question of, do I need these ridiculously high switching frequencies and operating frequencies? Will my device work at a lower frequency? And if the answer is yes, then just do yourself a big favor and use that lower frequency, because we saw there is a huge difference in the EMI performance of devices that operate at lower frequencies compared to higher frequencies. I mean, it's often thought that faster must always be better, but hopefully what today's video is kind of teaching you is that that is not always the case. For example, just imagine a scenario where you are designing a power supply and you had originally selected 1 megahertz for the switching frequency. Now, without going into too much detail about how the switching frequency impacts the design, just imagine if you were able to choose 500 kilohertz for your switching frequency and have no meaningful impact on the performance of your device. Doing so would have a significant impact in how well your device performed with its radiated emissions. It is important to understand the different trade-offs associated with selecting the operating frequencies of your digital circuits, but this is just one thing you need to be considering now. So the next type of noise that I want to talk about is, of course, the common mode noise. Now, dealing with common mode emissions can be challenging for a few reasons. The first reason is that common mode noise is actually quite difficult to wrap your head around and fully understand. Common mode currents aren't actually required in order for the circuit to function properly. So in an ideal world, you would eliminate all common mode noise and common mode currents in your design if possible. Common mode noise doesn't inherently have to do with any specific digital circuit, but there are some characteristics of these circuits that may make them more prone to generating common mode noise than other circuits. Another characteristic that makes common mode noise difficult to deal with is that it is not very easy to measure and monitor. And on top of that, there aren't a whole lot of solutions that we have at our disposal to deal with common mode noise. The main place that common mode noise will exist in your electronic system is going to be on the cables of the assembly. Essentially, what causes common mode noise is going to be a difference in ground potential between different parts of your system. So in other words, the quote unquote voltage drop from going from your digital circuit ground all the way to earth ground. For common mode radiation, we can use either a dipole or monopole antenna model. And we have this equation right here that represents the strength of the magnetic field that is generated by these two antenna models. F, of course, is the frequency of the signal, L is the length of our antenna, and I is the magnitude of the currents flowing on the antenna. Looking at this equation, we can see that there is a linear relationship between the length of the cable, i.e. the length of the antenna, the magnitude of the currents flowing on the antenna, as well as the frequency of the signal on the antenna. So we kind of got thrown a bone here where it's not like it's a quadratic relationship between the frequency of the signal. So that makes it a little bit easier to deal with. Another interesting thing to point out is that the shape of our cable has no impact on the EMI performance of it. So fundamentally, we have three main ways that we can potentially reduce our common mode emissions. That is, reduce the length of our cables, reduce the frequency of the signal that is flowing on the cables, or reduce the magnitude of the currents that are flowing on the cables. Now, usually we can't reduce the length of the cables in our system because that's kind of dictated by external requirements. So that leaves us just to focus on the common mode currents and the frequency of the signal. There are ways that we can tackle common mode emissions at all three levels of the design, including your circuit design, PCB layout, and the assembly level. At the PCB design level, the main thing we can do to combat common mode noise is to reduce the impedance of our ground plane as much as possible. In this case, the impedance of the ground plane refers to not only the resistance of the ground plane, but also the inductance as well. Remember that with EMI, you are usually dealing with frequencies that are in the range of the tens of megahertz all the way up to 1 gigahertz. So even a tiny amount of parasitic inductance can have a significant impact on your common mode emissions performance. The best way to minimize your ground plane impedance is to follow the PCB design best practices. So doing things like using multiple ground planes where you can. And one super important thing that you need to do is avoid at all costs putting any slots in your ground plane. At the circuit design level, there are a few different techniques that we can employ to reduce our common mode emissions. The first one is one that we previously mentioned, and that is to reduce the rise time of our periodic signals. As we saw with the differential mode EMI, adjusting the rise time of the signal has a significant impact on the harmonic content of the periodic signal. If you remember the graph that we looked at earlier, where the emissions started to level off past that breakpoint that was marked by the rise time of the periodic signal, well, you actually have a similar one with the common mode noise, except for it's actually even better in this case because we don't have a quadratic relationship between the frequency of the signal and the strength of the magnetic field that it generates. So in this case, we actually start out with a leveled off emissions envelope, and then at that breakpoint, it will start to decrease significantly. And of course, one of my favorite obvious strategies we can use to reduce our common mode emissions is, again, to just reduce the operating frequencies of our electronic circuits. Another way you can deal with common mode noise is to simply filter it. When it comes to filtering out common mode noise, there are specific filter configurations that you should utilize. One of the filter components is referred to as a common mode choke, and it is essentially just two inductors that share the same core. Each inductor carries current from two places. Typically, it's power and ground, but you can technically put this on any pair of signals. The way it works is that when common mode noise is present, the choke generates a magnetic field that acts as a significant impedance to the common mode noise. The choke thus chokes or suppresses the unwanted common mode current. As I mentioned earlier, you will usually see common mode chokes on power and ground traces, but you can actually put these on any communication lines or clock lines that you want to, and you kind of try out different things to see what works for your particular design. The best place to locate these common mode chokes is as close to the connector as possible, because as I mentioned, the common mode currents are usually present on the cables themselves. So this will allow your common mode choke to be as effective as possible by placing it as close to the cable as possible. Another way to filter out common mode noise is using a capacitor. So as I'm sure a lot of you are familiar with, a capacitor's impedance is inversely proportional to the frequency that it is observing. So with your super high frequency signals, it's going to act as a short circuit. Now, the key thing with using capacitors to filter out common mode noise is understanding what we're filtering them to. Because remember, common mode noise is a result of a voltage drop that goes between your digital circuit ground and your chassis ground. So in order to filter out common mode noise, we would place the capacitor between whatever signal line that you're trying to filter and our chassis or earth ground. This is actually why in some cases for like high voltage circuits, you will see a capacitor that is placed between the high voltage ground and earth ground, because it is also trying to filter out the noise that is present on that high voltage ground line. And we're trying to make a low impedance pathway to earth ground to reduce our common mode noise. One important characteristic of these EMI capacitors is that you need to make sure they have a very low equivalent series inductance. Because remember, as we just talked about, when you have really ultra high frequency signals in the tens of megahertz all the way up to 1 gigahertz, even a tiny amount of trace inductance can significantly impact the overall impedance profile of the capacitor. So minimizing your equivalent series inductance will help to make it filter noise much better. One technique I will often use to help reduce my ESL is to just place multiple capacitors in parallel, and that will also effectively reduce their ESL. There are also specialized capacitors such as the NPO type that are inherently lower in their equivalent series inductance compared to something like your traditional X7R ceramic capacitor. So check out those as well. The last type of change you can make to your design to impact the common mode noise is going to be at the assembly level. Now, as you heard me mention earlier in the video, I said that your PCB layout and circuit design are going to be the primary two areas you should focus because they are the most effective and low-cost solutions you can produce. Now, when it comes to common mode emissions, it's not always possible to get away with just doing those two things. Sometimes you need to go to the assembly level to try to address these problems. And so we're going to go over the different ways that you can address them at the assembly level. One of the main assembly level changes that you can make is to use a shielded cable. I don't want to spend an entire additional 30 minutes talking about the theory behind shielded cables, so I'm going to save that for a separate video. But the key takeaway here is that a properly shielded cable can significantly reduce your common mode emissions. The way it works is that it ensures that the common mode currents travel along the shield of the cable and not the actual conductors that are in your cable assembly. Another component you can add to your cable assembly is what's known as a snap-on ferrite. These are probably something that you've seen all around in the world of electronics, where you have a power supply that has this weird cylinder attached to the cable and you're not really sure what it's for. And the answer is it helps reduce your common mode emissions. These ferrites are very easy to use, and you can just literally snap them onto your cable assembly and immediately see if they impact your EMI. A lot of engineers kind of go to these, which kind of makes them controversial because some people look at it as a Band-Aid solution, while others kind of say that, it's effective and easy, so why not just use it? We'll actually cover how to properly use ferrites in a separate video, so just stay tuned for that. But that's just another option that you have at your disposal. And with that pretty much covers everything that I wanted to talk about in this video. Thank you so much if you made it to the end, and hopefully I will see you in the next one.